Electricity flows through wires. You know that. I know that. Everybody knows that. You flip a switch and electrons rush through the copper like water through a pipe, all the way from the power plant to your lamp. That is what they taught you, and it makes perfect sense. The wire is the highway. The electrons are the cars. The energy rides along inside the metal like passengers in a bus. And I'm telling you, right now, standing here in front of you, that picture is wrong. Not a little bit wrong. Not missing some details wrong. It is wrong in a way that once you see it, you cannot unsee it. The energy that lights your lamp does not travel through the wire. It never did. Now, I am not trying to be clever. I am not playing some rhetorical game. I want you to sit with that for a second. Every light bulb, every motor, every toaster, every radio you have ever used in your life, the energy powering those things did not come through the wire. And by the end of what I'm about to show you, you will understand exactly what I mean by that. And you will never look at a wire the same way again. Let me start where any sensible person would start. Let me start by telling you why the standard picture seems so reasonable. Because it does. It is a beautiful picture, and the people who developed it were not fools. You take a battery. You connect it to a light bulb with 2 wires. The bulb lights up. What happened? Well, the battery pushes electrons. Electrons are negatively charged particles, sitting inside the copper, 1 free electron per atom, just milling around. The battery creates a voltage, which is like a pressure difference, and that pressure shoves the electrons along the wire. They flow out of one terminal, through the wire, through the filament of the bulb, back through the other wire into the other terminal, a complete loop. The electrons carry energy from the battery to the bulb, and the bulb converts that energy into light and heat. Simple, clean, done. You can teach this to a 12-year-old. The current is the flow of electrons. The voltage is the push. The resistance is the opposition. Multiply the current by the voltage, and you get the power. It all clicks together like a jigsaw puzzle. And you know what? For designing circuits, calculating currents, choosing the right fuse, this picture works splendidly. Engineers use it every single day. And the bridges do not fall down, and the machines keep running. So why am I telling you it is wrong? Because something is hiding in that picture. Something nobody mentions in the first explanation. And once you see it, the whole thing falls apart like a sweater when you pull the right thread. Let me ask you a question. A very simple question. How fast do the electrons move through the wire? Most people, if you ask them, will say something like, well, electricity moves at the speed of light or close to it, so the electrons must be going pretty fast. That seems reasonable, does it not? When you flip a light switch, the light comes on immediately, not a second later, not half a second later, instantly. The moment your finger hits that switch, the room is flooded with light, so those electrons must be absolutely flying through the copper. Let us do the calculation. I love calculations, not because I love arithmetic, but because nature cannot lie to you through arithmetic. Take a typical piece of copper wire in your house, 12-gauge wire, about 2 millimeters in diameter, carrying maybe 10 amperes of current. That is a typical household current for, say, a hairdryer or a toaster. Now, copper, if you look at its crystal structure, has about 8.5 times 10 to the 28th free electrons per cubic meter. Let me say that number more carefully. 85 billion electrons in every cubic meter of copper. That is a staggering number. Each copper atom donates roughly 1 electron that is free to wander around the metal. The wire is absolutely packed with mobile charge carriers. The current, 10 amperes, means 10 coulombs of charge passing a given point every second, and each electron carries a charge of about 1.6 times 10 to the minus 19 coulombs. So if you work out how fast the electrons have to drift on average to produce that current through that wire, you get a number. And the number is about 2/100ths of a centimeter per second. 0.02 centimeters per second. Let me put that in perspective. That is about 1 inch every 2 minutes. That is slower than a snail. Considerably slower. A garden snail moves at about 1 centimeter per second, which is 50 times faster than the electrons in your wire. The electrons are moving at snail divided by 50 speed. If an electron started its journey from the power plant and tried to drift through the wire to your house a mile away, it would take the electron approximately 400 years to get there. 4 centuries. That electron would have started its journey in the reign of Queen Elizabeth I and still would not have arrived at your lamp. And here is something even more absurd. Those electrons are not just sitting still waiting for orders. Inside the copper, at room temperature, each free electron is bouncing around at enormous speed, roughly 1,000,000 meters per second, crashing into copper atoms, ricocheting off in random directions like a pinball in a machine gone haywire. That is the thermal velocity. It is huge, but it is random in every direction equally. So all that frantic motion cancels out and produces zero net movement in any particular direction. The drift velocity, the tiny crawl I just calculated, is the small bias layered on top of that randomness. Imagine a crowded train station where thousands of people are rushing around in every direction, bumping into each other, going nowhere on average. Now imagine a gentle breeze blowing from the east. Each person leans a tiny, tiny amount to the west as they walk. That lean is the drift velocity. The frantic rushing around is the thermal velocity. The lean is roughly 10 billion times smaller than the rushing, and yet because there are so astronomically many electrons all leaning together, that minuscule collective drift adds up to a current of 10 amperes, enough to run your toaster. So the electrons in your wire are moving fast, chaotically, violently, but going essentially nowhere. The net drift that constitutes the current is slower than a snail on a cold morning. So wait, pause, sit with that. If the electrons are barely crawling, drifting at less than 1,000th of a mile per hour, and yet the light comes on the instant you flip the switch, then the electrons themselves cannot be delivering the energy. Not by carrying it bodily from the power plant to the bulb. There is not enough time. The energy arrives at essentially the speed of light. The electrons are moving at the speed of a glacier. Something does not add up. That is your first clue that the standard picture is hiding something. Now, the usual response to this puzzle is actually quite clever, and I want to give it its due. People say, well, sure, individual electrons move slowly, but the signal propagates fast because the wire is already full of electrons. When you push one in at this end, one pops out at the other end, like a tube full of marbles. Push a marble in one end, and a different marble pops out the other end instantly. And that is a good analogy, up to a point. The electrical signal, the push, does propagate very fast through the wire, about 2/3 of the speed of light in typical copper. So there is a rapid chain reaction of nudging. You push one electron, which pushes the next, which pushes the next, and so on. And in a tiny fraction of a second, the nudge has traveled the entire length of the wire. But think carefully about what that analogy is actually telling you. In the tube of marbles, when you push a marble in one end, the kinetic energy has to travel through marble number 1 to marble number 2 to marble number 3. The energy propagates through the marbles, through the material of the tube's contents. Each marble pushes the next, and the energy hops from marble to marble all the way down the line. Is that really what happens in a wire? Is the energy hopping from electron to electron through the copper? And if so, there is a second puzzle, which is even worse. The energy in a wire flows in one direction, from the battery to the bulb, let us say. But the electrons in the wire are everywhere. They fill the entire loop. In one part of the circuit near the battery, you might say the electrons are giving energy. In another part near the bulb, the electrons are receiving energy and turning it into heat. But the electrons are all connected. They are all pushing on each other. How does the energy know to flow only from the battery to the bulb and not the other way around? The marble analogy breaks down. Something more subtle is happening. And the answer, when you finally dig it out, is startling. The energy is not in the wire at all. Let me back up and approach this from a completely different direction. Forget electrons for a moment, forget circuits, forget copper. Let me talk about fields. In the 1860s, working in his study in Scotland, James Clerk Maxwell did something that I think ranks among the greatest intellectual achievements in human history. And I do not say that lightly, I mean it. It belongs alongside Newton's laws and Darwin's theory. It changed everything. Before Maxwell, electricity and magnetism were two separate subjects. You studied one, then you studied the other, and there were some curious connections between them. Ørsted had shown in 1820 that an electric current deflects a compass needle, so electricity can create magnetism. Faraday showed in 1831 that a changing magnetic field can create an electric current, so magnetism can create electricity. But nobody had a unified picture. Nobody had asked, what are the rules for how these two phenomena dance together? Maxwell took 4 sets of relationships discovered by Coulomb, Ampere, Faraday, and others, and he unified them into a single coherent framework. 4 equations, that is all it took. 4 equations that describe how electric charges create electric fields, how there are no isolated magnetic poles, how a changing magnetic field creates an electric field, and how a moving charge or a changing electric field creates a magnetic field. But then Maxwell did something audacious. He noticed that his equations implied something nobody had asked for. They predicted the existence of waves, not sound waves, not water waves, a completely new kind of wave. An oscillating electric field creates a magnetic field. That magnetic field, as it changes, creates an electric field. And the two leapfrog each other forward through the vacuum, carrying energy as they go, needing no medium, no material, nothing but the empty void to travel through. The electric field generates the magnetic field, which generates the electric field, which generates the magnetic field. On and on, propagating outward like ripples from a stone thrown into a pond. Except there is no pond, there is no water. The ripples travel through nothing. Maxwell calculated the speed of these waves, using only the known constants of electricity and magnetism, and got a number, roughly 186,000 miles per second, 300 million meters per second. He recognized that number immediately. It was the speed of light which had been measured by other means. The coincidence was too perfect. Maxwell concluded with what must have been a breathtaking shock that light itself is an electromagnetic wave. Visible light, the stuff pouring from the sun, the stuff our eyes detect, is nothing more and nothing less than oscillating electric and magnetic fields traveling through space. That realization, published around 1865, unified optics with electromagnetism in a single stroke. And it had implications for circuits that people did not fully reckon with for another 20 years. See, once you accept that electromagnetic fields can carry energy through empty space, you are forced to ask a very uncomfortable question about a simple wire carrying a current. When current flows through a wire, there is an electric field associated with the voltage drop along the wire, driving the electrons forward. And there is a magnetic field circling around the wire, because moving charges create magnetic fields. Ampere showed us that. So around every current-carrying wire, you have both an electric field and a magnetic field existing in the space outside the metal. And Maxwell has just told you that electromagnetic fields can carry energy. So, are those fields around the wire carrying energy? And if so, how much? And in what direction? In 1884, a man named John Henry Poynting, a physicist at Mason Science College in Birmingham, England, sat down and worked out the answer. Poynting was not flashy. He was methodical, careful, thorough, and what he found would turn the standard picture of circuits on its head. Poynting derived a formula. You take the electric field at any point in space, you take the magnetic field at the same point, and you compute what mathematicians call the cross product of the two. The result is a new vector, a quantity with both a magnitude and a direction. The magnitude tells you how much energy is flowing through that point per second per unit area. The direction tells you which way the energy is going. This vector has come to be called the Poynting vector. It points in the direction of energy flow. People love that coincidence. It points, literally. Now, Poynting applied his formula to the simplest possible electrical situation, a straight wire carrying a steady current, and what he found was, to put it mildly, disturbing. Near the surface of the wire, the electric field has two components. Along the wire, there is a component parallel to the current, the field that drives the electrons forward. This comes from the voltage drop. But there is also a component of the electric field pointing radially outward from the wire, perpendicular to it. This comes from the tiny distribution of surface charges that accumulate on the wire to maintain the proper voltage gradient at each point along the circuit. These surface charges are not usually mentioned in introductory courses, but they are there, and they are essential. They steer the field inside the wire, and they create a field outside the wire too. Meanwhile, the magnetic field circles around the wire in loops, perpendicular to both the direction of current flow and the radial direction. Ampere's law tells us this. So you have an electric field with a radial component and an axial component, and a magnetic field wrapping circumferentially around the wire. When Poynting computed the cross product at the surface of the wire, the result pointed inward, radially inward, toward the wire, from outside. Let me make absolutely sure you catch the significance of this. The pointing vector at the surface of a current-carrying wire points from the surrounding space into the wire. The energy is not flowing along the wire. The energy is flowing from the outside space into the wire, perpendicular to the wire, from all around it. At a resistor, at a light bulb filament, the pointing vector plunges in from every direction, carrying energy from the surrounding electromagnetic field into the material of the resistor, where it is converted into heat and light. The wire is not a pipe carrying energy. The space around the wire is carrying the energy. The wire is more like a drain, soaking up energy from the field around it. I know what you are thinking. I can see it in your faces. Or, well, I can imagine seeing it because I have seen that expression many times. You are thinking, this cannot be right. This is absurd. And I want you to hold on to that feeling because it is an honest feeling, and it is exactly the feeling that the physics is fighting against. Oliver Heaviside, working independently in England at roughly the same time, reached the same conclusion. Heaviside was a remarkable character, self-taught, reclusive, cantankerous, brilliant. He took Maxwell's original equations, which were written in a sprawling, unwieldy form involving 20 separate equations, and he compressed them into the 4 compact vector equations we use today. The man essentially invented vector calculus as a practical tool for physics, and he was not shy about what the pointing vector meant. Heaviside said quite bluntly that the notion of energy flowing through the wire is wrong. The energy flows in the electromagnetic field. The wire is a guide, not a carrier, a guide. And Heaviside did not just say this in the abstract. He had practical reasons for caring. In the late 19th century, the great technological challenge was the undersea telegraph cable. These cables ran under the Atlantic Ocean, thousands of miles of copper sheathed in insulation, carrying telegraph signals between Europe and America, and they were a nightmare to operate. Signals sent from one end arrived at the other end, smeared out, distorted, weak. A crisp dot sent from London arrived in New York as a slow, mushy blob. Lord Kelvin, the most famous physicist in Britain at the time, analyzed the problem using the standard wire picture. He treated the cable as a kind of leaky pipe for electrical fluid. His analysis was useful but limited. But Heaviside looked at the same problem through the lens of fields. He realized that the signal was not really traveling through the copper. It was traveling in the electromagnetic field in the insulating layer between the central conductor and the ocean. The geometry of that insulating layer and the electrical properties of the materials determined how the signal propagated. Heaviside developed the mathematical theory of transmission lines, still used today by every electrical engineer. And that theory is fundamentally a theory about fields, not about electrons marching through metal. The irony is that Heaviside's work was rejected by the establishment for years. The Royal Society refused to publish some of his papers. He died in poverty. But his analysis was correct, and eventually the engineering world adopted it. Every time you use a coaxial cable, every time a signal travels through a transmission line, you are relying on the physics that Heaviside understood. The energy is in the field. Let me give you an analogy that I think helps. Think about a river flowing through a canyon. The canyon walls do not carry the water. The water flows between the walls in the open space. The walls shape the flow, constrain it, direct it. Without the walls, the water would spread out and go nowhere useful. But nobody looks at a river and says, the canyon walls are transporting the water. The water transports itself through the space that the walls create. A wire is like the canyon walls. The electromagnetic field is the river. The wire shapes the field, guides it, constrains it, makes it useful. But the energy is in the field, flowing in the space around the wire, not locked inside the metal. This is a complete inversion of the way most people think about circuits. And I want to dwell on it, because the implications are profound. Think about what a battery actually does in this picture. A battery does not inject energy into the wire the way a pump pushes water into a hose. A battery maintains a charge separation, positive on one side, negative on the other, through chemical reactions that forcibly move charges against the electric field. This charge separation creates an electric field. That field does not exist only inside the wire. It exists everywhere in the surrounding space, spreading outward from the terminals, guided by the surface charges on the wire. The battery sets up the field, and the field carries the energy. And those surface charges I keep mentioning, they deserve more attention because they are the unsung heroes of circuit theory. When a circuit reaches its steady state, tiny amounts of charge accumulate on the surface of the wire. Not inside the wire, on the surface. These surface charges are not uniformly distributed. There is a gradient, a steady change in the amount of charge from one end of the wire to the other, and this gradient is precisely what maintains the electric field inside the wire that drives the current. But those surface charges also create a field outside the wire, and it is that external field, combined with the magnetic field from the current, that creates the pointing vector. The surface charges are the mechanism by which the wire shapes the field in the surrounding space. Without them, the field outside the wire would have no structure, and energy could not flow in an organized way from source to load. This is a remarkably intricate arrangement. The battery sets up the initial field. The field redistributes the surface charges. The surface charges reshape the field, and the reshaped field carries the energy. It is a self-consistent, self-organizing system, and it all happens in a fraction of a second when you close the switch. The electrons inside the wire, they respond to the field. They drift, slowly, pushed by the electric field. Their motion creates a magnetic field around the wire, and the combination of the electric and magnetic fields is what the pointing vector operates on. The cross product of those two fields tells you where the energy is going. The electrons are not porters carrying suitcases of energy from the battery to the bulb. They are more like signposts or guardrails, maintaining the field pattern. They enable the field, they do not replace it. Now let me address the obvious objection, because I know it is coming. If the wire is not carrying the energy, you say, then why do we need the wire? Why can I not just take it away and let the fields do their thing? That is an excellent question, and the answer reveals the partnership between fields and matter. Without the wire, there is no closed circuit. Without a closed circuit, you cannot sustain a steady current. Without a current, there is no steady magnetic field around the wire. Without the magnetic field, the pointing vector drops to zero. No energy flow. The wire provides the path for the electrons. The electrons provide the current provides the magnetic field, and the magnetic field combined with the electric field creates the energy flow in the surrounding space. Take away the wire and the whole pattern collapses. It is like asking, if the river flows through the canyon and not through the rock, why do I need the canyon? Because without the canyon, the water spreads into a thin, useless sheet over flat ground. You need the channel to direct the flow. But notice something crucial. The channel directs the flow. It does not carry the flow. There is a difference. Let me push this further with a thought experiment that really drives the point home. It is a thought experiment that has driven physicists slightly crazy for over a century, and I think it is wonderful. Imagine a circuit with very, very long wires, a battery on one side, a light bulb 1 meter away from the battery, but instead of connecting them with a short wire, you connect them with two wires that each stretch 300,000 kilometers outward, loop around, and come back. Each wire is approximately the distance light travels in 1 second. The total wire length is about 600,000 kilometers. The wires go out to approximately the distance of the moon and then return. Close the switch. How long before the light bulb starts to glow? If the energy traveled through the wire, following the copper, it would have to traverse 600,000 kilometers at roughly 2/3 the speed of light. That would take about 3 seconds, maybe a little less, maybe a little more, depending on the exact propagation speed in the wire. But that is not what happens, not exactly. The moment you close the switch, the electromagnetic field begins to reorganize. The change in the field propagates outward from the switch at the speed of light in every direction. The light bulb is 1 meter away. In about 3/billionths of a second, the field change reaches the bulb, and as soon as the field arrives, energy begins to flow into the filament. The pointing vector at the filament surface becomes non-zero. The bulb begins to glow almost immediately, not at full brightness. Full brightness requires a steady state current in the entire circuit, and that cannot happen until the electromagnetic signal has traveled all the way down those long wires and come back. That takes seconds. So what you would actually see is a dim glow almost immediately, getting brighter over the next few seconds as the circuit approaches steady state. The initial energy arrives through the field, cutting directly across the 1 meter gap. It does not wait for the electrons to start moving all the way around the loop. The field gets there first. I should mention that the amount of energy reaching the bulb in that first fraction of a second is tiny, extremely small. The initial pulse is weak because the impedance of the circuit is enormous when it has not yet reached steady state, but it is not zero. And the fact that it is not zero is what reveals the truth about where the energy actually travels. Some people object to this thought experiment on practical grounds. They say no real circuit works this way, and the thought experiment is misleading. But that is missing the point. The thought experiment separates two things that normally happen together: the field reaching the load and the current being established in the loop. In a household circuit, where the wires are a few meters long, both happen in nanoseconds. You could never tell the difference. The thought experiment pulls them apart, so you can see them individually. And what you see is that the field gets there first, always, because the field is what carries the energy. One more thing about this thought experiment before I move on. It illuminates something about energy conservation that is easily overlooked. Where does that initial burst of energy come from? It comes from the electromagnetic field energy that was already stored in the space around the battery and wires even before the switch was closed. The battery just sitting there already has an electric field around it. When you close the switch, the field reconfigures, and some of that stored field energy propagates to the bulb. You are not getting something from nothing. The energy was already in the field, waiting. With the long wires, the mask comes off, and you see the truth that was always there. I want to go one step further into strangeness because Poynting's result has a consequence that borders on the absurd, and I think you should see it. Imagine a point electric charge just sitting in space. Next to it, a permanent magnet, both completely stationary. Nothing is moving, nothing is happening. The charge sits there with its radial electric field. The magnet sits there with its magnetic field. Static, silent, dead. Now compute the Poynting vector. Cross the electric field with the magnetic field, and what you get is a vector that circulates, energy flowing in circles around the charge and the magnet, endlessly, in loops, with no beginning and no end. Nothing is moving, no work is being done, no energy is being generated or consumed, and yet, according to the formula, energy is flowing in circles through empty space, around two objects that are just sitting there minding their own business. When I present this to students, some of them look at me as though I have lost my mind. And I understand why. It is a deeply weird result. Energy going around in circles forever. For no apparent reason. What kind of theory predicts that? But here is the part that should keep you up at night. That circulating energy carries momentum, real, physical, angular momentum. And if you try to disassemble the system, if you try to move the charge away from the magnet, you have to account for that angular momentum. It shows up in experiments. It has been measured. It is real. So the Poynting vector is not just a mathematical convenience. It is telling you something true about the physical world. The fields contain energy. They contain momentum. They are, in a very real sense, physical things. Not just mathematical abstractions drawn on a blackboard. Physical things that push, pull, carry, and flow. In my own lectures, I describe this whole business to the students, and I tell them, look, I know this sounds crazy. I say, our crazy theory tells us that the electrons are getting their energy to generate heat because of the energy flowing into the wire from the field outside. Intuition would seem to tell us that the electrons get their energy from being pushed along the wire, so the energy should be flowing down or up along the wire. But the theory says the electrons are really being pushed by an electric field that has come from some charges very far away, and the energy somehow flows from the distant charges into a wide area of space, and then inward to the wire. And I call it a theory that looks obviously nuts. Those are my words, obviously nuts. Because when you first encounter it, that is exactly how it looks. Energy sneaking sideways into the wire from the surrounding void. That is not how we imagine things working. But then you do the math, and the math works. Every single time. You compute the total energy flow into the surface of a resistor, and you get the current squared times the resistance. Exactly what Ohm's law says. You compute the energy flow out of a battery, and you get exactly the power the battery should deliver, watt for watt. No discrepancy, no fudge factors. That is the thing about physics. When the math works, you pay attention, and when it works perfectly, and it has worked perfectly for over a century, you change your intuition. You do not throw away the equations because they feel strange. You retrain your gut until the strange result feels obvious. Let me explain why this matters beyond the classroom. This is not just an academic curiosity for physics professors to argue about. Understanding that energy flows in fields, not wires, is the conceptual foundation for everything we do with electromagnetic waves, and it resolves some puzzles that the simple picture cannot touch. Here is one. In alternating current, which is what comes out of your wall outlet, the electrons do not even drift in one direction. They oscillate back and forth. At 60 cycles per second, the electrons wiggle back and forth by less than 1/100th of a millimeter. They go nowhere. They are vibrating in place. And yet somehow energy is steadily delivered from the power plant to your house. If you think energy is carried by the electrons, this is mystifying. How can particles that go nowhere deliver energy from somewhere? But if you understand that the energy is in the field, it makes perfect sense. The oscillating current creates an oscillating electromagnetic field. That field propagates energy outward from the source, through the space around the wires, to the load. The electrons shake, the field carries. The electrons are the medium that sustains the field pattern, but they are not the messengers carrying the energy. Take a radio antenna. An oscillating current runs up and down the antenna. This creates oscillating electric and magnetic fields. Those fields propagate outward through empty space as a radio wave, carrying energy. Miles away, the wave arrives at a receiving antenna. The oscillating fields push electrons back and forth in the receiving antenna, recreating the signal. The energy traveled through space in the field, with no wire connecting the two antennas at all. If you already understand that energy in a simple DC circuit travels through the field around the wire, then radiation is just the next step. The training wheels come off and the field goes out on its own, without any wire to guide it. But the principle is the same. The field carries the energy, always. A coaxial cable is another beautiful example. You have an inner conductor and an outer cylindrical shield. The electromagnetic field is contained entirely in the space between them. All the energy flows in that gap, that annular region of empty space. If you compute the Poynting vector in a coaxial cable, the energy flows parallel to the cable axis in the space between the conductors, not through the metal, through the gap, through what looks like nothing. That is why coaxial cables work so well for carrying signals. They are designed to contain and guide the field perfectly. The outer shield prevents the field from leaking out and prevents external fields from leaking in. The engineering of the cable is really the engineering of the empty space between its conductors. The metal defines the boundary conditions. It tells the field where to go and how to behave. But the field itself does the heavy lifting, carrying all the energy and information in that narrow ring of empty space. If you have ever wondered why the thickness and the dielectric material between the inner and outer conductors of a coaxial cable matter so much, this is why. You are engineering the medium through which the field travels. Change the gap, change the dielectric, and you change how the field propagates. You change the impedance, the velocity, the losses. The metal barely enters into it except as a boundary. Power companies know this too, even if they do not usually talk about it in those terms. High-voltage transmission lines are separated by large gaps. Why? Partly to prevent arcing, yes. But the separation also matters for the field geometry. The arrangement of the wires determines the structure of the electromagnetic field around them, and that field structure determines how efficiently power is transmitted. If you squeezed all the wires together, the field geometry would change, and you would lose more energy. Let me address one more subtlety, because I want to be thorough, and I do not want you to leave with a lopsided picture. Some people, when they first hear this, swing too far the other direction. They say, all right, the wire is not important, the field is everything. Throw away the wire. And that is just as wrong as the original misconception. The wire matters. It matters enormously. Without the wire, you cannot sustain the current. Without the current, you cannot sustain the magnetic field. Without the magnetic field, the Poynting vector is zero and no energy flows. The electrons, slow as they are, play a critical role. They maintain the configuration of the electromagnetic field. They are not the carriers of energy, but they are the maintainers of the channel through which the energy flows. Imagine the difference between a superconductor and a normal wire. In a superconductor, there is zero resistance. The electrons flow without any collisions, without any energy loss. The Poynting vector at the surface of a superconductor runs parallel to the surface, not inward. No energy enters the wire. All of it flows in the space outside. The superconductor is a perfect guide. In a normal wire with resistance, the Poynting vector tilts slightly inward. Some energy is absorbed from the field, converted to heat. The wire gets warm. The more resistance, the more the Poynting vector tilts inward, the more energy the wire absorbs. In a light bulb filament, the resistance is high. The Poynting vector plunges almost straight into the wire from all directions. Energy pours in from the surrounding field, is absorbed by the resistive material, and comes out as heat and light. That is what makes the bulb glow. The energy does not arrive through the filament from one end to the other like water flowing through a hose. It arrives from outside, from all around, pouring inward from the field. It is a partnership, you see. The field carries the energy. The matter shapes the field. Neither works without the other. The field without the wire dissipates uselessly. The wire without the field is just a dead piece of metal. Together, they create something marvelous. I think that is the most beautiful aspect of this whole business. Nature does not pick favorites between fields and particles. It uses both, intertwined, each enabling the other. Let me pull all of this together, because I have thrown a lot at you and I want the picture to be clear. The standard model of electricity says electrons flow through wires and carry energy from source to load, like water through a pipe. This model gets the right numerical answers for currents and voltages and powers. It is a useful tool, and it is not going away. But it is misleading about where the energy actually is and how it actually moves. The correct picture, the picture that comes from Maxwell's equations and Poynting's formula, says, the energy is carried by the electromagnetic field in the space around the wire. The field flows from the source, through the surrounding space, guided by the wire, and enters the load from outside. The electrons inside the wire play an essential role in maintaining the field, but they are not the energy carriers. The field is. This is not a matter of interpretation. It is not a philosophical stance. It is what the equations demand, and every experiment ever done is consistent with it. Now I know some of you might be thinking, well, who cares? If the simple picture gives the right answers, why bother with the complicated one? And that is a fair question. I will tell you why. First, because the complicated picture is the true one, and there is value in understanding how nature actually works, even when a simpler lie would suffice for everyday calculations. Knowing the truth changes how you think about things, it deepens your understanding, and it opens doors that the simplified picture keeps shut. Second, because the field picture is essential for understanding phenomena that the wire picture simply cannot explain. Radiation, antennas, waveguides, electromagnetic interference, fiber optics. Everything beyond the simplest DC circuits requires you to understand fields, and if you have been taught from the beginning that energy lives in wires, making the jump to fields feels like learning a completely new subject. But if you understand from the start that even in a boring battery and bulb circuit the energy is in the field, then everything else follows naturally. Third, and this is the one that matters most to me personally, because it is beautiful, the realization that the humble, invisible, seemingly empty space around a wire is in fact teeming with flowing energy. That is a glimpse into how nature really operates. It is the kind of thing that, once you see it, makes the world feel larger and stranger and more wonderful than it did before. And it connects to something even deeper if you want to follow the thread. The idea that fields are real, physical things, not just convenient mathematical bookkeeping devices, is one of the great transitions in the history of physics. Newton's gravity acted at a distance, instantaneously, with nothing in between. That always bothered people, and it bothered Newton himself. He called it an absurdity. But it worked, so people used it. Maxwell changed that. With electromagnetism, the field is the intermediary. The charge here does not reach out and directly push the charge over there. Instead, the charge here creates a field. The field fills space, and the charge over there responds to the field in its own neighborhood. Everything is local. The field is the messenger, the carrier, the medium, and it is as real as the charges that create it. When you look at a wire and think about the Poynting vector, you are touching that idea with your fingertips. The field between the wires is not nothing. It is something. It has energy. It has momentum. It has direction. It is doing something specific, measurable, and essential. The space around the wire is as full and as active as the wire itself. More so, in fact, because that is where the energy actually lives. I find that deeply satisfying. That the emptiness is full. That the nothing is something. That the most important part of the machine is the part you cannot see or touch. So here is the picture I want you to carry with you. The next time you flip a light switch, think about what actually happens. The switch closes. A charge redistribution occurs almost instantly along the surface of the wires, setting up the proper electric field pattern. That field, combined with the magnetic field from the current, creates a Poynting vector pointing from the surrounding space into the wire at every point. At the filament, where the resistance is high, energy floods in from the surrounding field, pours into the thin tungsten wire from every direction, heats it to incandescence, and light fills the room. The light in your room is not powered by electrons trudging through copper at a snail's pace. It is powered by invisible fields, filling the space around you. carrying energy at nearly the speed of light from distant generators through the empty air and converging on the glowing filament. Those fields are there right now. Every wire in this building, every cable, every cord is surrounded by an electromagnetic field carrying energy through the space you are sitting in. You cannot see it, you cannot feel it, but it is as real as the chair beneath you, and it is the real thing doing the work. I want to leave you with one last thought. People sometimes feel cheated when they learn this. Why did they teach me the wrong picture? They ask. But the simplified picture is not a lie. It is a model, and models are tools. You pick the simplest tool that does the job. For household wiring, the simple model is perfect. You do not need the pointing vector to wire a lamp. But if you want to understand, if you want to see behind the curtain, if you want to grasp how nature actually transports energy from one place to another, then you need the deeper picture. And the deeper picture is astonishing. Energy does not flow through matter. It flows